Hey guys, welcome to this video where we are solving the challenge from the end of the last video, which was to figure out what the electric field was at a symmetrical point that was z units away from a straight line of charge of length L. Alright, and so what we're going to be doing is using the steps from the last video to set up the integral, and then we'll actually solve the integral. So if you haven't watched that, go back and check it out because it will help make this make more sense. Alright, so conceptually what we're going to be doing here is we're going to say that this entire distribution of charge is contributing to the electric field. So what I'm going to say is this tiny charge element dq, right, at some distance r to the point is going to contribute a certain amount of electric field, we'll say dE. And every tiny piece of dq contributes a certain amount of dE as we work our way across the entire length of this rod. So the first thing that we could write about this is we could write the expression dE is equal to 1 over 4 pi epsilon naught times dq over r squared. And remember, this shows the amount of electric field that each tiny little dq element contributes at some distance r away. Now, the net amount of electric field is what we're trying to figure out. So we're going to add up all these little segments, right? And the first thing that we wanted to do from the last video's steps was write dq as the element lambda dx, because we wanted to change the q perspective to a geometrical perspective that still represents the same thing. So I'll go ahead and do that right over here. So I'm going to have d is equal to 1 over 4 pi epsilon naught times lambda dx over r squared. Okay. The next thing that we were encouraged to do was to look for symmetry, and we already described this as being symmetrical, over this axis over here. Now, why that's important is when we look at the electric field at this point, when we sum it all together, just using the visual electric field representation, right? Every little point along here contributes this horizontal component and a vertical component to the electric field. And we see that because of the symmetry, all of the horizontal components will cancel out and we'll only be left with vertical components. Okay, and the vertical component, right, is going to be, and I drew it a little longer just so we could see it easier, it's going to be the cosine of this electric field. So it would be dE cosine theta, right, at this point, because it would be adjacent over hypotenuse. So really what I'm doing over here on this side is I'm truly actually summing only the dE cosine components, or eventually will. And so what I'll do is just write the same thing over here on this side again. So 1 over 4 pi epsilon naught times lambda dx over r squared times cosine theta. All right, so I'm at this point now where I'm actually going to get rid of this because I'm really just adding up all these dE cosine components. And because I drew the arrow pointing away, that will say that this line of charge is positive. Okay, so the next step in the process is to do substitutions to this expression so that we have something that we can integrate. And we need things to be in all the same terms, right? So we have cosine theta, and the angle theta that we use, right, was opposite this one. This is changing as we work our way over x, right? As we work our way along here, the angle changes. Not only does the angle change, but r changes as well, right? And we're integrating over x. So there's too many things that are changing, and we'll need to write those out. Also, as a little side note, what I'm going to do in this video is instead of writing 1 over 4 pi epsilon naught 1,000 times, because we're not going to have any radial symmetry here with pi, I'm just going to change that to k, just to make this a bit easier. So remember, what we're going to do eventually is integrate both sides, add up all the pieces. So let's go ahead and write out some expressions for things in the equation so we can get rid of having so many variations. The first thing that we could use, right, at any dq position x away from the center, I'm going to say that r will change, but r can be written as x squared plus z squared to the 1/2, right? So just with Pythagorean theorem. Additionally, I can change cosine theta to be equal to, and we can look at it here as z over r, okay? And then r, of course, was all this, so I really have the expression z over x squared plus z squared to the 1/2 power. Okay, so now what I'm going to do is go ahead and substitute these back into this equation, and I'm not going to write the left-hand side anymore, which when I've integrated would just be the total e. So let me do that. So I'm going to say this all equals k times lambda times dx, okay, over, and we've got x squared plus z squared to the 1/2, and all of that is squared, right? Okay, and then that's times the cosine theta, which we showed was z over x squared plus z squared to the 1/2. So when simplified down, what I have is k lambda z dx over, remember this just becomes x squared plus z squared times x squared plus z squared to the 1/2, and what I get is x squared plus z squared to the 3/2. Okay, so at this point where I've gotten rid of as much as I can and got as many constants as I can, and now I'm actually ready to do some integrating. So that would be the expression that we would integrate across. And now I'm going to decide what my limits of integration are, and they have to be in terms of little pieces of x, right? And so what I'm actually going to do is, because this is symmetrical, I'm going to go from negative L over 2 here to 0 and then just multiply by 2. Okay, so I'll do that like so. All right, we'll go from 0 to negative L over 2 and then multiply by 2, and it only works because it's symmetrical. Okay, now at this point, if you were going to integrate this, we'd obviously pull out all of this stuff, right? All those constants. And then we'd actually be just left with this expression, which could alternately be written as x squared plus z squared to the negative 3/2 dx. And this has there's an identity, which we're not going to prove, but we have the expression, the integral of dx over x squared plus a squared to the 3/2, right? So there is actually an identity for that, and it's 1 over a squared times x over x squared plus a squared to the 1/2. Okay, so once again, we're not going to prove that, but we are going to use that identity to solve. Okay, so let's go ahead and do that. So we'll say k lambda z, and then we'll do the actual integration here. So I'm going to have 1 over my constant squared, so z squared, all right? And then that's going to be multiplied by x, okay, over, and then I have x squared plus z squared to the 1/2, okay? And this is evaluated from 0 to negative L over 2, okay? Or we could just do it to L over 2. In fact, let's do that. It doesn't matter either way, we'll just get a negative out the picture. Okay, so what I'm going to do at this point is I can plug in my values, right, in order to solve here, and then get some things simplified out. So the first thing that I would do here is I'm going to pull this constant over this side, and so we'll have k lambda z over z squared, which you can see is already going to have some simplification, which is great. And then I'm going to plug in my upper limit and then subtract my lower limit. Okay, so I'll do, my upper limit is L over 2 over L over 2 squared plus z squared to the 1/2. Okay, and then I can do the 0, but it would just all come out to be 0 because I'm going to plug in the 0 up top here and it's all gone. So I'll have this expression, okay, and now I'm going to do some simplifications. So I'm going to say k lambda, these z's will factor, okay, to this, and then I'm going to have this complex fraction. I'll pull the 2 down here, and I'm going to go ahead and just put it out front for right now. So that's going to leave me with L over L squared over 4, right, plus z squared, and all of this is going to be under the radical. Okay, so I'm at this point now where I have some bits and pieces, but this is pretty much the expression. Now what I can do is, because I'm going to say that lambda, it's a constant, so lambda is equal to q over L if the total charge of the bar is just defined as q. What I'll go ahead and do then is say k times q over L, right, times 2z, okay, times L over, and I'll write this as to the 1/2, so L squared over 4 plus z squared to the 1/2. We can factor out the L's, okay? And remember that in order to get the actual expression for the entire length, I have to actually multiply this by 2 because it's, we only did 1/2, right? So this would cancel, right? And so I can get even more simple here and say, and I'm going to move this out front, we're on top here, kq over z times L squared over 4 plus z squared to the 1/2. And this would give me the expression for the electric field, which is great. Now, something to think about here. If I were to compress the rod into a very small value, right? So if I were to push this either end in and they came down to 0. So basically what I'd be saying is if L went to 0, okay, so if I did this over a limit, what would happen here is this term would go to 0, right? And then this would be left plus z squared to the 1/2, so just z. Okay, so I'd be left with kq over z times z, which is just kq over z squared, right? That's as L goes to 0. So the electric field would be equal to kq over z squared, which we have usually written as 1 over 4 pi epsilon naught times q over r squared, right? And you can see that it actually does make sense. So the expression is correct, and that's a way to verify, because at z units away, which we could call r units away, it doesn't matter, as this thing truncated and compressed into just one little point, that would be the electric field due to a point charge z units away. And so we know that this expression must be correct.